This is the 8th talk about basic electronics for clinical neurophysiologists. The purpose of this talk is to explain some important concepts about filters and about analog to digital converters. This talk will be the first of a three-part series on these two very important components of neurodiagnostic equipments. The first talk of this three-part series will be conducted in two sections. The first section will follow a conversational format. The second will be conducted in a question and answer format. I will start by addressing three issues regarding filters during the conversational section of this talk. The first issue is the purpose of using filters. The second issue is the inner workings of filters. And the third issue is the type of filters we use in neurodiagnostic medicine. Filters are used for a simple purpose. The purpose of a filter is to see what we want to see better. That is, to make a wave, certain aspect of a wave, or a rhythm of interest stand out. This purpose is attained by using filters intelligently. When we do so, filters have the ability to reduce external interference, to eliminate out-of-band signals that, if allowed to go through the circuit of the equipment, would block further processing, to correct baseline offsets, to limit the frequency range under study, to prevent aliasing prior to analog to digital conversion, and to smooth the result of a process waveform. So now that we commented on the purpose for using filters in neurodiagnostic medicine, I would like to address the second issue: the workings of filters. Most filters used in neurodiagnostic testing work by decreasing the amplitude of specific frequencies by a predetermined value. I will explain this point further in the following frames. Let's say that a filter is presented with an activity composed of a wide range of frequencies ranging from 0.5 Hz to 100 Hz, but of similar amplitude, as I have plotted in this frame. And let's say that the filter specifications are such as to attenuate all 1 Hz activity 25%, 2 Hz activity 50%, 5 Hz activity 75%, 10 and 20 Hz activities 90%, and 50 and 100 Hz activity 100%. This being the case, the activity coming out of the filter should reflect the effects of the designated attenuation, and its plotting would look as depicted in this frame. In this frame, I have presented the input and the output of a filter with the characteristic just described. And in the lower segment of this frame, I have produce a cartoonish representation corresponding to the waves that would be produced at the level of the input and at the level of the output. In this new frame, I have represented the impact of a filter with different specifications than the one previously described. In this filter, contrary to the prior example, the lower frequencies are attenuated. The impact of the waveform is depicted below. In order for a filter to decrease the amplitude of specific frequencies by a predetermined value and to accomplish this task without significant distortion, the filter must have certain attributes. These attributes are an adequate frequency range so as to be able to analyze all the band frequencies of interest, a consistent phase linearity so as to be able to shift all frequencies by a constant time or not to shift them at all. In this frame, I have presented the function of a filter with good linear response under a happy phase. Please notice the yellow arrow. It represents that the increase in frequency is matched by a similar increase in time. By the side, under the sad phase, I have represented a filter with poor linear response. Again, notice the yellow arrow. In this case, you can see that the increase in frequency is not matched by an appropriate increase in time. I have added to this frame the representation of a spike and wave complex. The two elements are readily appreciated in the spike and wave complex by the side of the linear filter, but not so in the spike and wave complex represented by the side of the nonlinear filter. Another quality of a good filter is to produce little noise, so as to not contaminate the signal of interest with additional signals generated by the inner functioning of the elements used to construct the filter. And to have sharp definition, so as to provide a sharp demarcation between frequency you want to see and frequency you do not want to see. Another important attribute of a good filter is to have internal stability, as not to be influenced by changes in temperature or conditions internal to the equipment. And finally, the last important attribute of a good filter is to process information quickly. This is done as not to produce a delay between the input and the output of the signal. The last issue I like to address during the conversational segment of this talk is types, that is, major types of filters. The major filter types are analog. Analog filters accept as their input a continuous voltage versus time signal and produce at their output a continuous waveform. And digital filters. Digital filters operate on a discrete sample of the waveform and so require digitalization of the data by an analog to digital converter before filtering operation. Analog filters are made of electrical elements These elements are passive, implying that they do not require any external power. That is, that the transit of the amplified brain electricity is enough to drive the device. Analog filters made of such elements are called classical analog filters. Classical analog filters are, as I just told you, made of passive elements such as capacitors, resistors, and inductors. Analog filters can also be built using active elements. Active elements are those that require external power from a battery or a power source in order to operate. They are referred to as modern analog filters. Modern analog filters are made of active devices such as transistors and operational amplifiers. The benefits of modern analog filters over classical analog filters is that the modern analog filters can be more precise as to the band of frequencies they can analyze. For the rest of this talk, I will be mostly talking about classical analog filters. So, when I use the term filter without specifying analog or digital, classical or modern, I will be referring to classical analog filters only. Whereas when talking about digital filters, I will always use the term digital filters, and when talking about modern analog filters, I will also use the whole term. A good place to start talking about classical analog filters is to look at the schematic representation of an old EEG machine. Enclosed in the yellow box are three structures. They are pictorial representations of different types of classical analog filters. Classic analog filters were once used in most electrodiagnostic equipment. Classic analog filters are of three types: low frequency filters, high frequency filters, and 60 Hz frequency filters. 60 Hz filters are also called 50 Hz and notch filters. The latter term is used to emphasize the narrow frequency range of activity it is intended to eliminate. The term 60 Hz and 50 Hz frequency filters derives from their ability to eliminate the frequencies with which commercial alternating electricity is delivered to the electrical appliance. That is 60 Hz in the United States and 50 Hz in Europe. The three types of classical analog filters, low, high, and 60 Hz frequency filters, were very important components in the old analog pre-digital EEG machine world. Currently, the newer EEG machines, so-called digital EEG machines, only use modern, not classical, analog high-frequency filters. Yet, judging by the frequency of the questions in the neurophysiological boards exam about classical analog filters, you would think that they are still in high use. So, to keep up with the high numbers of questions about classical analog filters in all exams, I will discuss the three classical analog filters thoroughly. Classical analog filters are made of capacitors. Capacitors are a component of low frequency filters, high frequency filters, and 60 Hz frequency filters. Resistors are another important component of analog filters. They are a component of low frequency filters and high frequency filters. Inductors are yet another component of analog filters. They are used to build 60 Hz frequency filters. And the last, but certainly not the least important component of an analog filter is the ground. The ground in this figure is represented by the green line connecting all three filters. At this point, I will change from the conversational format to the question and answer format. And the first question is, in the classical analog high frequency filters, the capacitor is placed in the path of the current towards further processing and not in the path of the current to the ground. A, true; B, false. When considering the circuit of an EEG machine, it is customary, at least by some authors, to refer to the arm of the circuit where the current is traveling through the filter towards other processing elements of the equipment as the active arm of the circuit, and to the arm where current is traveling towards the ground as the ground arm of the circuit. Filters can be depicted as isolated structures maintaining this arrangement, that is, the existence of active arm and ground arm. So, the low frequency filter can be viewed as a capacitor in the active arm and a resistor in the ground arm. Low frequency filters are often referred to as LFF. A high frequency filter can be depicted as a resistor in the active arm and a capacitor in the ground arm. High frequency filters are often referred to as HFF. And a 60 Hz frequency filter. 60 Hz frequency filters can be depicted as an inductor and a capacitor in the ground arm of the circuit and no elements in the active arm of the circuit. So the answer to this question is false. Next question. Carlos Rich is a mnemonic for the position of capacitors and resistors in low and high frequency filters. A, true; B, false. At this point, I'd like to introduce to you a friend of mine. His name is Carlos Rich. He quit medical school to become a stock market day trader. In the next few minutes, I will tell you how this is related to filters. In this frame, you can see the three filters we have been talking about. They are labeled by their initials. A way to memorize the relation of the electrical elements in the low and high frequency filter is to remember the name of my friend Carlos Rich. The first name, Carlos, for low frequency filters, notice that Carlos has an L, which stands for low frequency filter. And the last name of my friend Rich for high frequency filters. Notice that Rich has an H for high frequency filter. The order of the letter in Carlos is the key for the mnemonic for low frequency filters. In a low frequency filter, the capacitor makes contact with electricity first, and the resistor is the second element. The order of the letters in Rich is also the key for the mnemotechnic rule for high frequency filters. The letter H stands for high frequency filter. The R indicates, since it is before C, that the resistor is the first element to come in contact with electrical current. And the C, since it comes after R, indicates that the capacitor is the second element. So the answer to this question is A, true. Next question. Which of the following structures below represents a low frequency filter? A or B? Remember Carlos Rich, the guy that quit medical school to become a stock market day trader. I hope you recall that you should use his first name to remind you of the order of the elements required to build a low frequency filter, which are also referred to as high pass filters. That is, a capacitor before a resistor makes a low frequency filter. So the answer to this question is A. Low frequency filters allow slow waves to go through the active arm of the circuit with minimal attenuation. A, true. B, false. So we know that low frequency filters, amicably called LFF, have in the classical configuration a capacitor in the active arm and a resistor in the ground arm. In this frame, I have added a wave with a peculiar configuration. I refer to this figurine as a single wave because it is above the baseline. The baseline is in this frame represented by the yellow line. Just below the wave, I have represented in a cartoon fashion the two types of contributing waves that add up to the formation of the original wave. I have represented thin and fat waves. The thin waves represent the fast wave and the fat waves represent the slow waves. Both types of waves contribute to the geometry of the original wave. I will use this representation to explain the concept of how filters work. In this case, how low frequency filters work. The capacitor, as you know from prior talks, will allow fast frequency waves to go through while limiting the passage of slow frequency waves. In other words, a capacitor will allow thin waves to go through with more ease than fat waves. In this frame, I have represented this phenomenon by drawing 4 thin waves past the capacitor, while only drawing 2 fat waves passing the capacitor. After going through the capacitor, the flow of the wave continues. But at this junction, the waves are faced with a choice: to continue in the active arm or to go to the ground arm. Since resistors are, as I hope you remember, equal opportunity elements, the same number of thin and fat waves will take the ground arm. As a consequence of this, more fast waves than slow waves will continue in the active arm. Thus, a predominance of fast wave will contribute to the ultimate geometry of the wave. So the function of a low frequency filter is to attenuate low frequencies wave more than high frequency waves. That is to subtract from the original waves more fat waves than thin waves. So the answer to this question is B, false. Next question. High frequency filters allow slow waves to go through the active arm of the circuit with minimal or no attenuation. A, true, B, false. In this frame, I am depicting an original wave with its subcomponent waves just about to start going through a high frequency filter. In this case, fat and thin waves go through the resistor. Remember, resistors do not discriminate. Once on the other side of the resistor, the current in the form of waves has to choose to continue in the direction of the active arm of the circuit or to take a detour towards the ground arm of the circuit. The capacitor will dictate the behavior of the waves, because by allowing more thin waves than fat waves to go towards the ground, it will allow more fat waves than thin waves to continue in the active arm. The end product is the production of a wave with preservation of amplitude and reduction of fast activity. So high frequency filters, by filtering out high frequencies, will allow slow waves to pass through the active arm of the circuit and contribute to the ultimate wave. So the answer to this question is A. Next question. In the classical analog low frequency filter, the larger the capacitor, the least the slow wave are attenuated. A, true, B, false. Low frequency filter attenuates slow wave the least when the capacitor is large, and attenuates a slow wave the most when the capacitor is small. So when presented with slow wave, a low frequency filter with a large capacitor will minimally attenuate the original wave. If the same size wave is presented to a low frequency filter with a smaller capacitor, the slow wave will be more attenuated. If the same size wave is presented to a low frequency filter with an even smaller capacitor, the slow wave will be even more attenuated. If, once again, the same size wave is presented to a low frequency filter with a tiny capacitor, the slow wave will be very, very attenuated. So the answer to this question is A, true. Next question. In the classical analog low frequency filter, the larger the capacitor, the more likely a medium-sized wave will not be attenuated. A, true, B, false. Low frequency filters with large capacitor do not attenuate medium-sized waves. Low frequency filter with small capacitors attenuate middle-sized wave the most. So when presented with a medium wave, the low frequency filter with a large capacitor do not attenuate the wave. If the same size wave is presented to a low frequency filter with a smaller capacitor, the wave is attenuated a little. If the same size wave is presented to a low frequency filter with an even smaller capacitor, the slow wave will be even more attenuated. If, once again, the same size wave is presented to a low frequency filter with a tiny capacitor, the medium wave will be even more attenuated. So the answer to this question is A, true. In the classical analog high-frequency filter, the larger the capacitor, the least fast frequency waves are attenuated. A, true. B, false. In the classical analog high-frequency filter, the larger the capacitor is, the larger the attenuation of fast activity will be. And accordingly, the smaller the capacitor is, the smaller the attenuation of the fast activity will be. Notice that at the end of the arrow, I have placed a green rectangle. It is this green rectangle that I am representing in the lower part of this frame. In it, I will introduce the fate of different size waves. Slow waves will not be affected by high frequency filters. Medium wave will be attenuated by high frequency filters with large capacitors. The larger the capacitor, the more the attenuation. But high frequency filter with small capacitors will not attenuate medium waves. High frequency filter will attenuate fast wave. The larger the capacitor, the more the attenuation. I make sense of this phenomenon regarding the capacitor size and attenuation of fast activity by high frequency filters by thinking that the smaller the capacitor is, the thinner the subcomponent waves have to be for them to be disregarded towards the ground. Hence, relatively more fast wave will be available to go through the active arm of the circuit and contribute to the ultimate wave geometry. So the answer to this question is A, true. Next question. The degree of filtering of a 1000 millisecond wave by a 1 Hz low frequency filter depends on the filter's A, roll-off, B, cutoff, C, common rejection mode, D, all of the above. In order to understand how filters work, we must define two concepts: cutoff and roll-off. The cutoff of a filter labels the filter as high or low frequency filter. The cutoff of a filter represents the frequency at which the amplitude of a wave is reduced by the filter to 70% of its original size. So a filter that reduces a 100 microvolt 1 Hz wave to 70 microvolt is labeled a 1 Hz filter. The choice of 70% reduction was made to label the filters because a 70% reduction in amplitude of a wave represents a 50% drop in the power of a wave. I think of the cutoff as the pivotal point to describe the actions of a filter. In this frame, I have represented the cutoff as an aqua dot of which I will make use when answering the next question. So the answer to this question is B. Next question. The cutoff of a filter is the frequency at which the amplitude of a signal is 3 dB down from its original amplitude. A, true, B, false. We have just mentioned that the cutoff is the point at which the original amplitude of a wave is reduced to 70% of its value. This degree of attenuation corresponds to 3 dB down from the original amplitude of a wave. So some authors talk about cutoff of a filter using dB as a unit. So the answer to this question is A. Next question. The cutoff frequency of a filter can be given as A, percentage, B, dB, C, time constant, D, all of the above. The cutoff of a filter can be given as a percentage of amplitude drop, as dB, or as time constant. So the answer to this question is D, all of the above. Remember that percentage-wise, a cutoff implies a reduction to 70% of the original amplitude. In dB, a 3 dB down from the original amplitude, and in time constant, a decay by a factor of 0.37. Next question. Time constant represents the time it takes for a wave to rise or drop by dash percent. A, 31, B, 42, C, 63, D, 90. Time constant represents the time it takes to charge a capacitor and a resistor 63%, or to be discharged to 63%. The 63% is used because time constant is defined as 1 minus 1 divided by E. E is a constant used in mathematics. The value of E is 2.718. This number is the base of natural logarithm. It was chosen because it varies very little despite the increasing value of n. You can see in this figure that going from 10,000 to 100,000 to 1 million makes very little change on the number. So the execution of the operation in this frame, that is dividing 1 by 2.718, is 0.3679. That when subtracted from 1 yields 0.6321. So it was rounded to 63%. So the answer to this question is C, 63. Next question. Time constant is mostly used to describe the effect of low frequency filter on A. Square waves. B. Sine waves. C. Square and sine waves. D. Fast waves. Time constant from a pure physics point of view represents the time it takes for a resistance capacitor circuit to charge or discharge 63% of its ultimate value. In EEG lingo, time constant is linked to the functioning of low-frequency filters and the behavior of square waves. The lower the time constant, the sooner the square wave drops to 37% of its original value. As you can see, while looking at this frame, it takes longer for a signal to reach 37% of its original value when the time constant is 0.16 than when the time constant is 0.033. Let's say you have a square wave of 2¼ seconds. As you can see in this frame, I have represented time in seconds by using different colors. Now I have introduced percent of reduction, and now the percentage drop required for a one-time constant. The way to determine the time constant of a wave consists of drawing a horizontal line from the 63% point, and at the point where the horizontal line you have just drawn cuts the drop in wave, there you draw a vertical line towards the base of the wave. The number cut by this vertical line represents the time constant of the given wave, in this case 1 second. So looking at this wave, we should say that the time constant is 1 second. The relation between time constant and value of a filter is often asked in the board exams. Remember that a time constant of 0.16 seconds has the same effect on a wave as a 1 Hz low frequency filter, and a time constant of 0.033 seconds corresponds to a 5 Hz frequency filter. An analogy often made is that time constant behaves like a door. The thinner the door, the thinner a wave has to be to go through it. So the answer to this question is A. Next question. The degree of filtering of a 2000 millisecond wave by a 1 Hz filter depends on the filters A. Roll-off, B. Cutoff, C. Common rejection mode, D. All of the above. I will start answering this question where I left off when I answering the question about cutoff. You remember I told you that the cutoff was the pivotal point in understanding filters. I refer to it as the pivotal point in addition to being an important point to understand filter because it serves as a fulcrum for the roll-off. I like to think of the roll-off as a line pivoting at the cutoff point, as I have shown in this frame. To our misfortune, the degree of tilting of this line is given in a dB per octave unit. To our fortune, the only thing we need to know about it is that the less inclined is the line pivoting on the cutoff, the higher the number of dB per octave. So in this frame, I have given this roll-off the value of 6 dB. This one with a bigger incline, a value of 3 dB, and this one with less incline than the one with 6 dB, a label of 12 dB. I will reiterate this point while looking at this frame. As you can see, the steepness of a 3 dB is less than the steepness of a filter with a 6 dB per octave roll-off, and the steepness of a 6 dB roll-off filter is less than the steepness of a filter with a 12 dB roll-off. Most EEG machines use roll-off of 12 dB, thus giving a sharper roll-off and better control on the frequency of the wave we want to see and the waves we do not want to see. So the answer to this question is A. Next question. The percentage of reduction of a wave lasting 1 second when using a 2 Hz low frequency filter depends on the dB per octave roll-off of the filter. A true, B false. In this frame, I am introducing a line representing Hertz. As you can see, the values are placed in an ascending fashion. Just below this value, I am introducing other values. These values correspond to milliseconds. And just below them, I am introducing a third type of values in seconds. This is starting at the value corresponding to 0.1 Hz. This line represents the x-axis of the chart that I will use to show the percentage of amplitude reduction of a wave produced by filtering. As you can see, the percentage of the amplitude to which a wave will be reduced is expressed in the y-axis of this chart. I have completed the chart in this frame by making a grid using frequency and percentage of amplitude to which a wave will be reduced to. If we use a 2 Hz filter, which would reduce a 2 Hz wave to 70% of its value, a 1 second wave will be reduced to a value of less than 70% of its original value. Let's say 37.5%, or even more, let's say 25%, depending on the roll-off of the filter. Remember, when we spoke about roll-off, we spoke about slopes. The slope of a 6 dB per octave frequency filter has a certain steepness to it, where the steepness of a 12 dB per octave is more pronounced. So the answer to this question is A, true. Next question. If a 1 Hz low frequency filter with a roll-off of 6 dB per octave attenuates a 2-second wave to 17% of its original value, a 1 Hz low frequency filter with a roll-off of 12 dB per octave will attenuate a 2-second wave to -% of its original value. A 70, B 30, C 7, D 99. I will use this figure again to answer this question and to illustrate the relation between cutoff and roll-off. The question states that a 1 Hz low frequency filter, which as you know will reduce a 1 second wave to 70% of its original amplitude, with a roll-off of 6 dB will reduce a 2 second wave to an amplitude of 17%. In this frame, I have introduced a red dashed line. This line represents the imaginary slope resulting from using a low frequency filter of 1 Hz with a roll-off of 6 dB per octave. The second part of the question is what will happen to a 2 second wave if instead of using a 1 Hz filter with 6 dB per octave roll-off, we were to use one with 12 dB per octave roll-off. We know that the slope of a 6 dB roll-off is less steep than the slope of a filter with 12 dB per octave. I have represented the imaginary effect of a 12 dB per octave roll-off by adding a caramel color dashed line to this figure. In this frame, I have indicated its value by placing an aqua dot at the intersection of the caramel dashed line and the 2 second wave, which in this case corresponds to about 7%. So the answer to this question is C. Next question. If a 1 Hz low frequency filter with a roll-off of 6 dB per octave attenuates a 500 millisecond wave to 85% of its original amplitude, a 1 Hz low frequency filter with a roll-off of 12 dB octave will attenuate a 500 millisecond wave to -% of its original value. A 5, B 30, C 70, D 95. Here you see represented the degree of reduction a filter with the given characteristics produce on a 500 millisecond wave. In this chart, I have indicated by drawing a caramel line the degree of reduction produced by changing to a filter with 12 dB per octave. So the answer to this question is D. So as you can see, analog filter with high octave per dB allows you to better eliminate the wave of the duration that you do not want to see and keep the wave of the duration that you want to see. If a 20 Hz high frequency filter with a roll-off of 6 dB per octave attenuates a 20 millisecond wave 10%, how much would a 20 Hz high frequency filter with a roll-off of 12 dB octave attenuate a wave with similar duration? A 20%, B 30%, C 10%, D 95%. The last few questions were about low frequency filters. This question is about high frequency filters. And again, when we talk about filters, we need to talk about cutoff and roll-off. The problem states that when using a high frequency filter of 20 Hz with a roll-off of 6 dB per octave, a 20 millisecond wave will be reduced to 10% of its original size. And as we change the roll-off of the filter to 12 dB, what would the amplitude of a 20 millisecond wave be? The answer to this question is 1%. C. Next question. In addition to dB, another unit to indicate the steepness of a roll-off is poles. A true, B false. The term we have so far used to refer to the filtering of frequencies neighboring the cutoff point has been roll-off. Another term used to refer to the filtering of frequencies neighboring the cutoff point is filter order. When this term is used, then the steepness with which the neighboring frequencies to the cutoff are eliminated is given by the number of poles assigned to the filter. Using this nomenclature, we just need to remember that a filter with the order of 6 poles produces a steeper elimination of unwanted signals than one with 4 poles, and that a filter with the order of 4 poles produces more steep elimination of a wanted signal than one with 2 poles. So the answer to this question is true. Next question. Transitional band or region is considered a key filter parameter. A true, B false. Take a few seconds to look at this frame. Notice the cutoff and the steepness of the roll-off. I will use this figure to describe 3 key filter parameters. The first parameter I would like to describe is the motive of this question, that is, transitional band. The term transitional band refers to the frequencies whose amplitude are partially attenuated by the filter but not totally obliterated by it. I have represented these bands in yellow. The term stop bands refer to the frequencies that are totally obliterated by a filter. I have represented these bands in red. The term passband refer to the frequencies that are not attenuated at all by a filter. I have represented this band in green. So the answer to this question is A, true. Next question. The transitional band or region that occurs as a consequence of using a filter with a roll-off of 12 dB per octave is wider than when using a filter with a roll-off of 6 dB per octave. A, true, B, false. In this figure, the yellow band indicates the transitional band. Notice its width and compare with the next frame. As you can see, in this frame, we have presented a 12 dB octave filter. This figure depicts a wider transitional band when using a filter with a 6 dB per octave roll-off. So the answer to this question is A, true. Ripples in finger lingo means variations in amplitude in the passband or stopband. A, true. B, false. To answer this question, I will use one of the figures we have just looked at. This figure represents the function of a filter with no ripple. The stop of the passband is flat and straight, as you can see. In this frame, I am representing ripples in the passband. Ripples in the passband attenuates wave with frequencies you do not want to attenuate. The floor of the stopband is also flat and straight in this figure. In this frame, I am representing ripples in the stopband. Ripples in the stopband introduce to the wave frequencies you do not want to be included to the final morphology of the wave. So the answer to this question is true. Next question. Which of the following filter family has a steeper roll-off? A, Bessel. B, Butterworth. C, Chebyshev. D, elliptical. We have so far talked about three attributes of filters. We have talked about type of filters, cutoff frequencies of filters, roll-off frequency of filters, and now we're going to talk about the fourth attribute. The fourth attribute has been called transfer function or filter characteristic. Based on the difference in types of transfer function, 5 family of filters have been listed. Bessel, Butterworth, Chebyshev, inverted Chebyshev, and elliptical. They differ in transitional bands and ripples. Ripples can occur in the passband and in the stopband, as we have just previously mentioned. Butterworth has a thick transitional band and no ripples at the passband or stopband. Chebyshev has a thin transitional band and ripples in the passband, but no ripples in the stopband. Chebyshev inverted has also a thin transitional band and has ripple in the stopband, but no ripples in the passband. Elliptical has the thinnest transitional band, but has ripples at both ends. So the answer to this question is D. Next question. Notch filters are labeled according to their cutoff. A, true. B, false. So far we have said that the cutoff of a filter, whether a low frequency filter or a high frequency filter, defines the filter. This is not the case with notch filters. Notch filters are labeled according to the frequency they attenuate the most. In addition, notch filters have a very steep roll-off. Going back to the chart that I have so often used in this talk to illustrate the effects of filters, I will bring it back in order for me to show you the effects of 60 Hz notch filters. A 60 Hz notch filter affects activity of about 16.6 milliseconds. This is the duration of the activity most affected by a 60 Hz notch filter, while the neighboring activity is attenuated by much less percentage. Digital filters do an even better job in restricting attenuation to the wave lasting 16.6 milliseconds, which correspond to 60 Hz electricity. So the answer to this question is false. This concludes the first of the 3-part series about filters and analog to digital converter. Thank you very much for your attention.